Hello and welcome to REconsidered, a new podcast series from Swiss Re.
Climate change is certainly playing a role. It's here. We have to deal with that.
I'm your host, Sherry Elliker. In this series, we will talk about some of the most pressing issues related to climate change and its impacts on our society, economy, and environment.
What we won't see is snow.
We will also discuss how the insurance industry and other stakeholders can work together to reduce the risks and increase the resilience of our communities. Today, I'm joined by Dr. Davide Ferranda, a climate scientist and research director at the French National Center for Scientific Research, and Swiss Re's severe convective storm lead, Elizabeth Victor. Today, we will focus on the topic of severe convective storms, or SCS, which are storms that produce hail, tornadoes, strong winds, and heavy rain. These events have been causing more and more damage in the U.S., across Europe, and other regions. So stay with us as we dive into the world of risk reconsidered. Davide and Elizabeth, it's good to be with you. You both look at storms, one from the perspective of a climate scientist and the other from the perspective of an insurance company. But I think your disciplines intersect with each other because you're both interested in understanding big thunderstorms and the perils associated with them. Why are thunderstorms so hard to forecast?
I think one of the major challenges that we're facing when we look at severe convective storms is that they're usually small scale and very short-lived. It's a very small phenomenon, so it's just difficult to capture that in modeling because you need to have a really high resolution to capture that. So we are still trying to understand what physical features are working together there. We're still learning about that.
So, Davide, let me put this another way. Why is assigning causal factors contained under the label climate change to severe convective storms so complex or murky? Or is it?
These thunderstorms are small-scale phenomena, and we have to think that for weather resolution model, we can have a resolution up to 1 kilometer, and that can resolve these cumulonimbus clouds that are responsible for thunderstorm. But at the climate level, we need to perform simulation for much longer time. That is over 30 years, over 100 years. And to run these long simulations, we cannot afford in terms of computational power, in terms of economical cost. So we need to have larger grids. And the grids are as large as regions such as Sicily or Corsica. So too big to resolve the clouds, too big to resolve this phenomena.
If I can add something.
Of course.
If we try to look back and learn from the past and how severe convective storm has developed over time, that is also a real challenge because we don't really have consistent observations or a comprehensive set of observations. In areas where there's more people, you naturally have a higher number of reported storms versus areas where there's less population and you just miss a lot of those events.
So I guess the million-dollar question is climate change having an impact on severe convective storm activity? Davide, what do you think?
The answer for this question is yes. Global climate change is having an impact on severe convective storms. The difficult question is to answer how. And for this, we have already some elements that we can understand from our knowledge of the physics of the climate. And the first element is the simplest one. Global warming increase the temperature all over the world, so increase the possibility of having warm and wet conditions close to the ground. The fuel for thunderstorm and severe convective storm is increasing with climate change.
And Elizabeth, from your perspective, is the idea that climate change may be contributing to severe convective storms a controversial view, that climate change is playing a role?
Well, climate change is certainly playing a role. It's here, it's impacting weather. We have to deal with that. From an insurance perspective, it's just very important to understand how big these influences are and how big these influences are on the timescales that we are interested in. Our view is that it's still quite tough to determine what the impact of climate change really is, especially on the loss perspective, because if you think of the loss, you have to include a lot more factors, and hazard or the way that frequency and severity of severe convective storms is changing is just one component of that.
2023 was a year of very heavy damages. From an industry perspective, what were the drivers?
So that's really interesting. In 2023, severe convective storm caused $64 billion in insured losses globally, and that's a record high. And more than half of all insured cat losses came from SES. And if you look into just the SES losses, about 85% came from the US. And this year that actually continued. So in the first half of 2024, we saw $42 billion in insured losses due to SES. And that accounts for about 70% of all insured cat losses globally in the first half of this year. We certainly see that the SES losses have increased over recent years, both in Europe and in the US. And in the US, we particularly see that if we look at year-to-year increase in SES losses, over the last 15 years, we've seen an annual increase of about 8%. And if we dive a little deeper to understand what the drivers really are of that increase, we start to realize that, first of all, inflation is making a big impact. Inflation specific to construction cost. But beyond that, we also have to take into account that the economy is growing, population is growing. So due to urbanization and spatial expansion, we see larger losses. For example, areas that are quite prone to severe convective storms, such as Texas, there we've seen quite a big population growth. That also impacts the losses that come from that region. And finally, we also see that vulnerabilities are changing. An example that's very easy to picture is that the number of solar panels that are being installed on roofs is increasing. So there are a lot of different factors that drive these losses. And somewhere in there, there's certainly also an aspect that is driven by climate change. But for now, from our perspective, if we look at the losses, the major contribution is coming from these economic factors.
So it really sounds like, at least for now, the damage that we've seen from big thunderstorms is really a combination between human factors and storms that strike in the right spot. What lessons can we take from this?
What we learned from that is that it's really important to understand the exposure. Do we understand the sum insured? Do we know whether the values that we get are actually the latest values that we need to take into account? If we look at the inflation environment, that is really a point that is very dynamic. These values are changing rapidly, so it's good if we have a handle on that.
And Elizabeth, it would seem that insurers would really want to keep track of this growth in exposures. But Swiss Re has recently written about how the initial damage estimates basically tripled to $6 billion from the Italian hailstorms of 2023 alone. What happened?
So that phenomenon is called loss creep, and it affects the entire insurance and reinsurance industry. For example, in the floods in Germany in 2021, we saw in the end the loss creeping by a factor of 2. There were hail events in France in 2022 where we saw the losses creeping by a factor of 1.5. And as you say, now in Italy, there was almost a factor of 3. And the main reasons really link back to the point that I made before, that there was a considerable underestimation of the underlying exposure. We weren't really getting the latest information on insured values, so we couldn't account for the full impact of inflation. For the insurance industry, it is important to be a lot more disciplined in how we report and handle exposure.
Perhaps people would be surprised to learn that public policy actually has a lot to do with damage trends. Can you give us some insights?
Specifically relating to that event in Italy last year, we realized that there was a specific government program going on that incentivized the introduction of solar panels and the way they insulated houses. So the way these houses were built or how vulnerable they actually were to hail had changed in many households, but that information was not actually part of the exposure information that was provided to reinsurers.
Davide, you've written about the 2023 storms in Italy. What was it about those conditions that made that summer a particularly costly one for Italy?
Well, it's in all the news since like 14 months now, and it starts in 2023. We are reaching the global warming threshold level of 1.5 degrees Celsius. That was the threshold not to overcome to limit the extreme events such as severe convective storms that can affect our society. And 2023 was extremely hot in the Mediterranean. There is also another important point that we have to make. The increase also in terms of really the physical potential damage that this storm can produce. It's not something that is linear in terms of temperature, in terms of humidity. What I mean is that increasing 1 degree more the temperature of the Mediterranean or the Atlantic Ocean or the Pacific Ocean will make this storm not 1 point more severe, but can be 10, can be 100, can be 10,000, depending on the indicators that we are looking at.
I'd like to get an opinion from both of you with this. We're learning a lot about the role climate change is potentially playing in such events. Are we simply at the mercy of the weather, or can we do something about it?
Well, there are two things that we can do right way. One is reducing the CO2 emissions where we can. And in fact, there are lots of activities that can now run on renewable energies. So this should be our priority when we can do it. And the second point is adaptation. Elizabeth mentioned that we have several problems that when we have a severe convective storms increase the damage. One is the fact that the population is growing. One is the fact that the number of buildings is growing, and the number of buildings is growing sometimes in places where it shouldn't, like near a river, in a valley that is prone to get flooded.
One thing that fascinates people is the dimensions of hail. If you're from Texas, it's baseball-sized hail, and I read about near soccer ball-sized hail in Italy. Do you see any evidence that hailstorms may not only become more frequent, but also produce larger hailstones with the potential to do more damage? What do you think, Elizabeth?
So if we think of a warmer atmosphere, that means that there's more power in the atmosphere. So there's stronger updrafts related to severe convective storms. Also because we have higher instability, that means that there's potential that hailstones grow to a larger size within the cloud. They can become larger and heavier before they actually are so heavy that they fall down. At the same time, though, because the atmosphere is getting warmer, the melting layer is also rising up a little bit, meaning that once the hailstone starts falling down, there's a longer way that the hailstone has to go through falling down, where it's so warm that it could melt before it hits the ground. So the small hailstones are becoming less frequent, most likely, because they will melt before they hit the ground. So there are a few things that compete with each other in all these processes. And there are a lot of uncertainties around how that will pan out, especially also on a regional scale. There's a lot of variability how exactly that will turn out.
Davide?
Elizabeth mentioned the solar panels. We have to plan well where we install the panels, if it's an area that is subject to this kind of event or that can be subject of this kind of events in the future. From the point of view of the societies, even the public actors that have to decide where to install airports, solar panels at large scale, railways, hospitals, it's very important to know how this phenomenon will evolve in 20 or 30 years.
I'd like to stop you there because I just had an interesting conversation with a scientist and storm chaser from Ohio State University about destructive tornadoes. Hi, Professor Jana Hauser. How are you?
I'm fine, thank you, Sherry.
Thank you so much for joining us. You're a meteorologist at Ohio State University who uses radar to observe and understand supercell thunderstorms and tornadoes. In addition to advising film crews on tornadoes, you also work with other universities, helping them create storm-chasing courses.
Yeah, that's correct. My first tornado chasing experience was as a junior in college when I was going to Penn State University, and I've really never looked back. Fast forward a few years as a professor myself now, I have the privilege of executing my own courses.
I actually see quite a few storm chasing programs at colleges and universities for meteorologists. Are courses like these getting more popular?
The answer is yes. One of the major reasons for this is because there's documented evidence to suggest that when students learn through experiential learning, going out and doing a storm chasing course, it is much more impactful on their education. This provides an important tool that we can tap into as college professors to allow our students to actually have the experience of not just learning book smarts, but also having direct application of the information that they're learning. For many of these students, this is their first experience actually seeing some of these really big thunderstorms and potentially tornadoes. I tend to encourage my students not to gauge success on whether or not we see a tornado, but more about the whole process of learning the nuances, the ins and the outs of forecasting, of the logistics of being in the field.
When you go in the field to chase storms, use mobile radar equipment to capture data about supercells and tornadoes.
Radars are an incredibly important tool to addressing and querying the tornado and the storm and the dynamics and the inner workings. It's almost like taking an X-ray of the storm because we can see precipitation three-dimensionally. We can see motion in the air towards or away from our radar. And when you couple multiple radars together, you can actually triangulate the air motion and come up with a three-dimensional wind field so that you get an understanding of not just the horizontal flow, but also the vertical movement of the storms. And some of these storms have incredibly strong upward vertical motion, pushing 100 miles per hour of upward motion. In Greensburg, Kansas, in 2007, there was an F5 tornado, and it literally sucked up a fire hydrant, and there was like 6 feet of piping underneath that fire hydrant. So you can imagine it's going to take a whole lot of upward motion, and it wasn't bent. It was like it was plucked up out of the ground like a weed. So the mobile radars allow us to really decipher the inner workings and especially the flow fields within the storms. Where does rotation come from? What's the trajectory of the air that's going into the tornado? Where is it coming? Where is it going? And all of these pieces of information we can use to put together the large-scale puzzle of what makes a tornado tick and why do they form in the first place.
Another very fascinating thing about what you do is that you work with movie producers. There is a new Hollywood movie about tornadoes. Now, this has at least contributed to a discussion about the relationship between climate change and tornadoes. First of all, as a scientist, what can you tell us about this complex topic?
Absolutely. So the link between climate change and tornadoes is a little bit difficult to establish, namely because climate change is related to processes that are large scale in both space and time. And tornadoes, on the other hand, are very isolated and local events. And despite our notion and the sense we get from the media, they're actually relatively rare. So to put this connection together between an entity which is lasting at most an hour and is at biggest maybe 2 miles with the large-scale climate system, which is global in context, and we're looking at timeframes over at least hundreds of years to put things into context from a climate change scenario, it's a very difficult problem to address. What we do know is that there appears to be a consistent trend in both intensity and in numbers of tornadoes across the United States, looking at the U.S. as a whole and looking at the year as a whole. In fact, we might actually be seeing a slight decline in the number of very intense tornadoes. The challenging part is that our record is short and there are considerable contaminants in our record. So putting all those pieces together creates a mucky, muddy situation. But what we can say in terms of climate change is that we are seeing evidence of changing geographies of where tornadoes are occurring. So less frequent tornadoes in the central parts of the U.S., particularly in Texas, and more tornadoes in places like the southeastern United States, up through the Midwest, and even over into New England. Some of that is unclear about how robust that signal is because we have, again, that short time frame. But it does appear that places such as New England and heavily populated areas in the northeastern U.S. and into Philadelphia, Washington, D.C., New York City metroplex might be seeing more tornadoes in the future. So those areas where we might experience more should definitely be taking precautions and be thinking about that in the context of their own community and community resiliency plans.
When you are contacted by a movie studio to help with a particular movie, how much do they really want to know about the inner workings, or is it more about the optics of what's it going to look like?
My role with the filming of Twisters was to serve as a meteorologist for a film crew. I was contacted by a cinematographer named Sean Casey, who was asked to provide background footage for the new Twisters movie. So my role was to basically get him to where he needed to be to get the footage that he needed, which was for background green screen type footage that would occur behind the actors.
Have you seen the movie?
I did, yes. I saw the movie just this past weekend.
And what'd you think?
It was a combination. I had to turn parts of my science brain off to appreciate it. But I will say that they did do a good job with the research side of things. They talked to individuals from the National Severe Storms Lab. They even had their actors and their film crew come in for a brief Weather 101 crash course that was taught by one of the directors of the National Weather Service. And they had consultants from the Storm Prediction Center. I would say 75% of the science was pretty decent. There were a couple cringy moments there for me, one of which my particular area of expertise is the process of forming tornadoes. And we know using rapid scan radars that tornadoes form from the ground upward and not from the cloud to the ground, which is contradictory to what your eye sees with the funnel cloud. In terms of the actual tornado, there's usually tornado strength winds at the ground first before the funnel cloud actually connects to the ground. But there are multiple references of tornadoes touching down, which is a phrase that just I tell my students I'm going to whip their hands with rulers like the old school days. There were a few moments like that. And the premise of destroying a tornado, which is a really big, important part of their narrative here, is just physically not realistic. Even if we were able to do this, it would be requiring so much material. It would be environmentally unfeasible to try to deploy silver iodide.
Is there anything at all that we can do to influence tornado behavior?
When we look at the tornadoes themselves, we really can't modify where the tornado is going. The storm is going to be driven by the overall winds in the atmosphere, as well as some of its own internal mechanisms. There are internal processes to the storm itself that have self-perpetuating tendencies, and the storm feeds on itself in a sense. And changing that is really not feasible in any capacity. So our best bets are to try to engineer structures to withstand the anticipated tornado winds that could possibly happen. And this, unfortunately, often implies that we have to build more expensive structures.
So these tornadoes really, they're going to be there. If this is the case for communities that may be impacted or impacted more frequently by tornadoes, what do their leaders and residents need to consider in order to prepare?
Basically, everybody east of the Rockies should consider tornadoes a real threat to their community because we just don't know when and where they're going to happen. Most importantly, for your own personal safety, everybody should have a tornado plan in action in terms of where you would go in your place of work or where you would go in your home. You want to put as many walls between where you are and the outside of your house. We need to be preparing ourselves and preparing structures to hold up to these EF2s, maybe EF3s, because more likely than not, that would be the intensity that you would expect to potentially impact a structure.
So if we can't stop the tornadoes themselves, it sounds like we need to do a better job of living with them. Is that the approach?
Yes, that's absolutely the approach because it's nature.
So when are you going to go back out and chase some storms?
I have several field campaigns, so this is going to the science side of chasing, that are hopefully underway. As early as spring 2026, I will be getting my own mobile radar, so I'll be taking that into the field for data collection purposes. I also have a class that I'm revamping at Ohio State University and hope to get students in the field for the spring of 2025. And then I have some tricks up my sleeve for trying to hopefully get myself out there just for personal enjoyment so I can be a spectator as well, because the science is great, but it also adds a layer of decision making that's not present when you can just go out and have fun.
It's funny what your definition of fun is, because a lot of people would say that's the furthest thing from fun to me. Thank you, Professor Hauser. Please stay safe.
Well, thank you so much, Sherry. It has been a pleasure.
Okay, fascinating work from Dr. Hauser. Davide and Elizabeth, what do you think? Do you think that future weather will be extreme enough to make storm chasing vacations a lucrative venture for entrepreneurs?
I discourage anyone who's listening to start do storm chasing. I think what is very important is when there is a warning issued by a weather agency, wherever you are in the world, for a severe convective storm, we have to respect this warning, and we have to think that severe convective storm can have altogether this hazard. So it can be electric hazard with lightning, can be a tornado, can be hail. And we have to think all of this hazard can happen in the same storm.
Davide, in your work, you examine how greenhouse gas emissions may be influencing weather extremes. Cold spells, heat waves, cyclones, and severe thunderstorms. You've done attribution work on major extremes: 2021 flooding in Germany, Winter Storm Philomena, the Po Valley tornado outbreak, and even so-called metacanes, the fierce hurricane-like storms in the Mediterranean region. Can you see any common denominators between these extreme events?
Yes, we have the evidence that most of the recent events, and when I say most, I mean about 95% of the events that we have analyzed, they are already affected by anthropogenic climate change. And they are already impressive in terms of quantity of rain, quantity of lightnings, large sites of hailstorm that are produced. I think what I've learned from doing these attribution studies of extreme events to climate change is that we are very vulnerable and we are not prepared for most of the events that have affected even highly developed countries such as Germany, such as the US, such as Italy.
Elizabeth, one thing that's really interesting about your work is modeling. Your teams can take sophisticated data and determine the factors that drive losses. Can you speak a little bit to what goes into modeling updates like those Swiss Re has advocated for to reflect evolving risks, including from hail?
The most sophisticated models that we use usually follow a concept that is based on 4 components: on a hazard component, vulnerability, exposure, and the financial conditions that are very specific to insurance. And the hazard component provides a distribution of the frequency and the severity of a specific peril, for example, hail. And often we start with historical parameters that explain those distributions, but then we enhance them to expand the time period that we look at using stochastic methods. And history thereby becomes only one possible realization of what can happen physically. So we basically add thousands or even tens of thousands of additional simulations to that historic one to represent what could happen. And when we do this, we make sure that we take into account all available scientific findings on if and how these frequency and intensity patterns are shifting, or whether they're changing in any other way that we need to take into account to represent a forward-looking view, which means for us about a 5-year horizon. And then if we look at vulnerability and exposure, as mentioned before, it's really important to stay up to date, to include the possibility for newly emerging vulnerabilities like solar panels, but also to understand the latest trends and dynamics in the market regarding the insured value, and then act quickly and use the advantage that we at Swiss Re have that is a little unique, that we develop these models in-house so we can react really swiftly to any trends or dynamics that we see.
I'm really curious about this. Is there anything particular about our changing weather and its destructive potential that keeps you up at night?
What is really making me worried is the huge inequalities that are building up in front of these extreme events with respect to the populations. The vulnerability is changing, and Elizabeth mentioned it, but in a way that is absolutely in a disproportion between rich and poor people. So I think that we should all try to address fairly this question and, of course, to try to protect the vulnerable population. And I think in this we are all together because we just live in a better world.
Elizabeth, insured losses are part of the equation, of course. But what about the total damage? It's much higher than simply the insured losses. Are people really adequately protected?
There's a lot of advancements regarding mitigating losses. Warnings before events, for example. On the one hand, actually from insurance companies to tell you to drive your car in the garage or to pull up the blinds. In addition, what's relatively new is that also, for example, the American Society of Civil Engineers has released a new standard for protecting buildings for tornado damage in 2021. And in 2024, it was actually added to the International Building Codes. So far, it's still non-binding, but it's still a step in the right direction. And it certainly helps to make people more aware that there are ways that they can strengthen their buildings, especially for the weaker tornadoes, for example, that happen much more often than the very, very strong ones. And for hail, there's similar recommendations that are being developed. So the Insurance Institute of Business and Home Safety, for example, is driving a lot of these efforts in the context of their Fortified Home Program standards. But none of these building standards at the moment are binding. So the proportion of properties that actually follow these recommendations is still pretty low. And it's also really difficult to assess how many buildings actually are prepared.
Davide, at least according to the 2015 Paris Agreement, the planet must be at net zero emissions by around 2050. If you could look into your crystal ball, what do you think Europe's weather is going to look like in 2050?
Well, first of all, we can say that this is not going to happen according to the policies that are in place now and that have been implemented at a global level. Unfortunately, we are aiming at a rise in temperature that could be of the order of 2 degrees by 2050, even more in the more pessimistic scenario. So the weather that we expect in 2050 is a more extreme weather where hailstones are bigger, where we have Mediterranean cyclones more intense, where we have heat waves that are prolonged over the entire season. Is a bit already what we are seeing now. We could take summer of 2023 or the summer 2024 and project it in the future because these summers have been already very hot, much warmer than the global average. What we won't see is snow. We'll see snow at very high mountain levels. So this is also challenging because there are many activities in Switzerland, for example, but also in the Alps that are linked to the snow, not only tourism, that is the first thing that we think, but also the water, everything that is linked in the water of this basin where there are tens of millions of people living are linked to the snow.
And Elizabeth, Swiss Re discussed the importance of making sure that they keep pace with evolving weather phenomena as well as insured exposures. How is that going?
Well, it's crucial for the insurance and reinsurance industry that we have as much high quality information as possible on the properties that we're insuring. And that includes an adequate valuation of the insured asset. But in addition to that, it's also really important for us that we have a well-rounded and up-to-date understanding of the hazard as well, and really understand how that is developing and what's driving these developments.
Davide Ferranda, Elizabeth Victor, thank you so much for your time, your expertise, and a fascinating conversation. Thank you for listening to the first episode of Risk Reconsidered from Swiss Re. Stay tuned for more episodes coming up soon.